this is a quick review of the second part of the basic statistics concepts that are key for this course. So let's talk about the most famous model, the normal model. And what is the normal model? It's a bell shape, as you know, unimodal and symmetric. A normal model for every mean and standard deviation. These are the parameters. Mu, which is the center of the curve that we will see shortly, and sigma, which represents the spread. That is the population standard deviation, and this is the notation that we are familiar with. So here is the way the curve is this perfectly bell curve, symmetric, around the mean, mu, and every value, every normal model can be standardized. In other words, move it to 0 using the C-score that we learned about last time. So for this particular curve, it's well known. This was proved many years ago. 68% of the area below the curve are within 1 standard deviation from the mean, 95% within 2 standard deviations from the mean, okay, and 99.7% for 3 standard deviation. It's unlikely, and it's considered what we will consider an outlier to be 5 or 6 standard deviations away from the mean on a normal model. How do we check for normality? Because every assumption that we make, we should check, verify using the data. We can do histogram and see if they resemble a symmetric unimodal bell curve distribution. Of course, we discuss how histogram can change depending on how we decide on the beam width. But there is a plot which is called the normal probability plot or QQ plot. We plot each value of our measurement, variable that we have, the measurements, against the C-score that would be expected at the distribution being perfectly normal. If the plot shows, so we will look to see a straight line or nearly a straight line, then the normal model works. If the plot strays from being aligned, then the normal model is not a good model. So let's see this data right here that is portrayed in this histogram is fairly, looks fairly symmetric, right, around this. So we will tend to think, okay, of course there are some deviations here in these two lower ends of the observations here that we have. So the QQ plot looks like this, and you see here are these smaller values, but overall we said, okay, we can assume the normal model is appropriate. Okay, so the histogram is unimodal and somewhat symmetric except for the skewness. Now let's look at here where we do have a skewed distribution and look how the normal probability model looks. So here we will not say, we might consider doing a transformation like the ones we have looked. Now, R has functions for different probability distribution models, and the instructions always start equal. With a P, a Q, we have D and R. So what is that? P is for probability cumulative functions. So we will get the cumulative probability. Q is for quantile, the inverse cumulative distribution function. D for the density, the probability that the random variable equals that value, which doesn't make sense in the case of to use it except to plot the density function. And R is when we want to simulates, get random measurements for understanding. So, for example, all the famous probability distribution, we can get these probability calculations on R very easily. Of course, there are parameters that we have to take care of, but we have all of this. We will use a lot the student t distribution, the normal, of course. We use a lot the F distribution, the features F, the chi-square, all of this. For the normal, P norm give me this, the cumulative probability, right? The distribution function P of x less than or equal to x, while Q norm give me, so for Q norm is the, give me the quantile, right? In other words, it gives me the case such that the probability that x is less than or equal to k is that value that I put as the probability. This instruction gives me the 95 quantile, in other words, or the 95th percentile of the distribution. Now, what is really important for us, now let's discuss, this is wrong, sampling distribution. When we use a statistic like y bar, we need to know and understand what results are there. So the sampling distribution, it gives me the result that I'm looking forward to. In simulation will mean if we were sampling many times from the same population and computing a y bar and then putting all of those y bar together in a graph and see what do we expect, okay? Now there are results. So Central Limit Theorem, the most famous theorem for us, right? If a population has mean mu and standard deviation sigma, then the sampling distribution of y bar, I mean, if I were repeating this sampling distribution, this is the result that I will see. So this has mean mu and standard deviation, but let's look. So the same center, in other words, y bar is an unbiased estimator of the mean, but the standard deviation of y bar is smaller than the standard deviation of the population that we are sampling from. It is divided by the square root of the sample size. The larger the sample, this becomes smaller. The shape of this sampling distribution is more nearly normal than is the shape of the population, unless we were sampling really from a normal distribution. But so as you learn, this theorem is the most useful. We had a rule of thumb, right? N greater than 30 to satisfy the conditions of the Central Limit Theorem. Now let's think for a moment, y bar minus mu, what is that? It's the error in using y bar as an estimate of mu. The standard deviation is the typical size of that error, right? Gets smaller, and then this, because it is divided by the square root of n, gets smaller as n increases. It is the best guess, the standard error, the best guess about the likely size of the difference between a statistic used to estimate a parameter and the parameter itself. Standard error are ordinarily calculated by substituting estimates of variability parameters into the formulas, okay? For y bar, it is, what am I going to do? It's sigma over the square root of n, so we estimate sigma is usually, what do we call, the sample standard deviation, capital S. And with that, there are a measurement that we need to report, which is the degrees of freedom associated with every standard error. Okay, we are going to estimate many parameters. Here we are estimating mu, right? But mu will have, I get the sample, right? Estimate, which is y bar. And then what happened to this y bar? Y bar has a sampling distribution that has the standard deviation sigma over the square root of n, and we estimated with S divided by the square root of N. The degrees of freedom are measured in units of equivalent numbers of independent observation. N minus 1 degrees of freedom is where we divide S in the case of Y bar. Okay, now the C ratio, estimate, this is an estimate minus parameter divided by the standard deviation of the estimate. For example, here, this will be the C ratio for Y bar. Of course, then what happened? Most likely we don't know sigma, so we will estimate and the Z ratio becomes something else. The T ratio that I have here. So I didn't know sigma. Let's say I'm going to replace it by S and I get the T ratio. Okay, and of course, there are going to be degrees of freedom associated here because they are the degrees of freedom of the standard error, which is N minus 1. The T ratio when sampling from normal in a random sample of size N from a normal distributed population, the sampling distribution of its T ratio, Y bar minus mu S divided by square root of N has a student T distribution on N minus 1 degrees of freedom. Shape of the T distribution is very similar. You cannot tell apart from a normal. The T distribution has a symmetric unimodal. Okay, I'm going to show you pictures. There are different T's depending on the degrees of freedom, and the black one is the standard normal. So when N becomes large, the T and the normal are impossible to tell apart. Otherwise, when N is small, you see here I have heavier tails than the normal 0, 1. We use this in the confidence interval estimate. When sigma is known, this is my confidence interval. We get, remember this portion here, the margin of error. So, which is calculated when we know sigma with the C star coming from the normal 0, 1 times the standard deviation of the sampling distribution, which is that. But most likely we will not know sigma, so then we will compute the margin of error slightly different using the T. Of course, we will get all of this using software, but we need to understand this is how the margin of error is computed. The T ratio for the two samples, we will start reading the examples from chapters 1 to 3, and they are all about using the T ratio. Okay, so we make the assumption, there are several assumptions different between two independent sample averages. So here, the assumption that we are going to make is that the individual standard deviations are equal, so they are equal to sigma. Independent samples of size N1 and N2 are taken from two normal distribution. So the sampling distribution of the difference will be approximately normal with mean difference of the mean and standard deviation, then calculated under this expression. So I have, because I am assuming the two sigmas are equal, so this is sigma, but then, of course, we will not know this, we will estimate it. And how do we estimate? Using the pool. We are going to use both samples to get an estimate of that sigma parameter. And it is this expression that seems scary, but it isn't. So it's just pulling from the two samples. From each sample, we compute the deviations from the particular Y bar for the individual two populations, and then we combine this into this formula and the confidence interval. This is how the margin of error gets computed. The T statistic will be built in a similar fashion. This is the hypothesized difference. Most likely will be assumed the difference. There is no difference, so 0. And this is all for this little refresher of your basic statistics course.